everyone. So today this lecture is going to be about energy in simple harmonic motion. So I have a few questions here that we're going to go over. So first and foremost, where does the mass here have no velocity? Now here we can see as this mass on a spring goes back and forth, oscillates between the positive amplitude and the negative amplitude, at those two amplitude points, which we can call turning points, the mass stops and it turns around. So we can see that at those points, we have a brief moment of no velocity before we then turn around and the sign of velocity changes. So this occurs at the two amplitude points or the two turning points. So where does the mass then have no kinetic energy? Well, if we have no velocity, we have no kinetic energy because we know that kinetic energy is 1/2 times mass times velocity squared. So if V is equal to 0, then kinetic energy is also equal to 0. So that also occurs at the two amplitude points. Now at those points then, what kind of energy does this mass have? Well, we can see that this energy is transferred from kinetic energy at that equilibrium position to then potential energy at the two amplitude positions. And because we have a mass on a spring here, this is elastic potential energy. So we have elastic potential energy. Now, of course, if we had something like a pendulum that's swinging back and forth, that pendulum would have gravitational potential energy up at that certain height. Okay, so it does matter what kind of simple harmonic oscillator we're talking about. But in this case, because there's a spring present, we have elastic potential energy at the two amplitude points. So another question, where does the mass have maximum velocity? Well, we can see here, again, at the two amplitude points, we have no velocity. And then as we go toward that equilibrium position, the velocity and the force are in the same direction. So since the force is also pointed in the direction of velocity, acceleration is pointed in the direction of velocity. And we know when velocity and acceleration are pointed in the same direction, the object is going to speed up. Now, as soon as that mass hits the equilibrium position, then the velocity is still pointed in the same direction, but the force is actually pointed in the opposite direction because this is a restoring force. It wants to restore that object back to the equilibrium position. So because force is pointed in the opposite direction, that means acceleration is pointed in the opposite direction, and therefore the mass slows down. So that means the maximum velocity is going to occur at that equilibrium position because as we go toward equilibrium, we speed up. As we go away, we slow down, and then at the amplitudes we're 0. So you can see the block speeds up, slows down, 0, speeds up, slows down, 0. All right, so at the very center, that equilibrium position, we have a maximum velocity. So therefore, where does the mass have maximum kinetic energy? Again, that will be at the equilibrium position. Now, another question here, where does the mass have a maximum acceleration? Now, we know that acceleration is proportional to force from Newton's second law, right? Force is equal to mass times acceleration. So where we have the maximum force, we will have the maximum acceleration. Now, if we recall from chapter 8, our spring force equation is force is equal to negative kx, that's Hooke's law. So that means that force is proportional to displacement. So the farther we are away from equilibrium, the greater the force and therefore the greater the acceleration. So therefore, we're going to have maximum acceleration at the two amplitude points because we're the farthest away from equilibrium. Now, where do we have a minimum acceleration? Again, because force is equal to a negative kx here, when x equals 0, so at our equilibrium position, force equals 0, and therefore acceleration equals 0. So our minimum acceleration occurs at the equilibrium position. So these are some, basic things to know about energy in simple harmonic motion. So really make sure that you understand, where velocity is 0, where acceleration is 0, where we have maximum kinetic energy, where we have maximum potential energy. Because if you understand those things, then you're really going to be able to understand energy in simple harmonic motion. Now, of course, we know that with energy comes conservation of energy. So what's going to happen here, and you saw that with that little, GIF that was on the last slide. As this mass oscillates back and forth, we're going to oscillate back and forth between potential energy and kinetic energy. Now, even though we're oscillating back and forth between potential and kinetic energy, the total energy is staying the same. Okay, so we can see here that our energy at the 2 amplitude points, so a negative amplitude max or x maximum and a positive x maximum, our kinetic energy is the lowest at the amplitude points and our potential energy is the highest. However, the combination of the two is always going to be the same because we have a conservation of energy. Now, this graph right here is just showing the potential and kinetic energy as we go through an entire period. Okay. Now, like I said before, as the mass is oscillating back and forth, the amount of potential energy and kinetic energy in the system change, but the total energy remains constant. So if you recall from our conservation of energy unit, we had total energy initial equals total energy final. And if we plug in our initial kinetic plus potential energy, that's going to equal our final kinetic plus potential energy. And then when we're talking about a mass on a spring, we can then plug in our kinetic energy equation and our elastic potential energy equation to get this right here. So you can use this equation in these simple harmonic motion problems with a mass on a spring. Now, another way that we can do this here, I'm going to kind of derive a expression for finding the total energy of a system. So if we start with our potential energy as a function of time, we know potential energy, this is elastic potential energy, and that is equal to 1/2 times kx squared. Now for x, we know that we have a equation for the position as a function of time, which was our x maximum times the cosine of the phase, which is omega times time plus the phase constant. Now what happens here is we plugged that in for our position and then had to square everything because of course it's position x squared in the potential energy equation. So we squared all that. We then did the same thing for kinetic energy, but instead of position, of course, we have velocity because it's 1/2 mv squared. So we plug in the velocity function as it changes with time for our simple harmonic motion and then square everything because velocity is squared. And then if you recall, we had that m omega squared is actually equal to the spring constant k. So because of that, we're just inserting k in for m mass times omega angular velocity squared. So we insert that k in there. Now, if we add those two things together, we can see that we're getting an equation for the total energy. So total energy of the system is equal to potential energy at any time t plus kinetic energy at that same time t. And then here what we're going to do is we're going to factor out that 1/2 kx maximum squared. And so we end up getting this, and we can see that cosine squared of the phase plus sine squared of the phase just equals 1. So because of that, we then can see that the total energy of the system can be measured as just 1/2 times kx maximum, which is the amplitude position, squared. So if you know the spring constant k and you know the amplitude, then you can find the total energy of the system this way. And of course, when that block is at the maximum x position or the amplitude position, all of the energy, all of the total energy, that is all in potential energy. So this makes sense to us, right? There's no kinetic energy at that point. So kinetic energy is equal to 0, and therefore total energy is equal to maximum potential energy. This also tells us that total mechanical energy is independent of time t, which is really important, okay? Because we see that there is no time in this equation. Now, for a block on a spring, we can also just use this equation, like I said before, for our total energy if we know the velocity at any point and then the position at that same point. So this is for any point, not just at the amplitude position or at the equilibrium position. However, we know that at the equilibrium points, we have a maximum velocity there because we have maximum kinetic energy and no potential energy. So you can say that total energy is equal to our maximum kinetic energy at the equilibrium point, and that is equal to 1/2 times mass times velocity maximum squared. And then at the amplitude points, like we said, all the energy is in potential energy. So maximum potential energy is 1/2 times our spring constant K times the amplitude squared. Now, because these are both equal to our total energy, we can set them equal to each other, which is what I'm doing down here. So if we set those things equal to each other, we can cancel out that 1/2. And then if we solve for maximum velocity, then we get this equation that's on the bottom right here. So if you know your spring constant K, your mass, and your amplitude, you can find the maximum velocity using this equation.